गुड मॉर्निंग बच्चों। आज हम जो टॉपिक डिस्कस करने जा रहे हैं वो है मोलर हीट कैपेसिटी। ये थर्मोडायनेमिक्स में इसका काफ़ी यूज होता है। यहाँ पे हमने कुछ टर्म्स लिखे हुए हैं, कैपिटल सीपी एंड कैपिटल सीवी। एक्चुअली दीज आर द मोलर हीट कैपेसिटीज एट कांस्टेंट प्रेशर एंड एट कांस्टेंट वॉल्यूम। और यहाँ पे जो लिखा है दैट इज हीट सप्लाइड एट कांस्टेंट प्रेशर QP इक्वल टू स्मॉल m इंटू स्मॉल CP इंटू डेल्टा T। यहाँ पे m क्या है, दैट इज द मास ऑफ द गैस, mass of gas taken, and small cp is the specific heat। small cp को हम बोलते हैं specific heat capacity, specific heat capacity of gas। और इसी तरह से qv is the heat supplied at constant volume and this is mass of the gas, cv is the specific heat at constant volume and delta t is the rise in temperature of the gas। okay, and here we have written and Cp delta T। Here Cp is the molar heat capacity at constant pressure and N is the number of moles of the gas taken, and similarly Qv is the heat supplied at constant volume। It is equal to N, that is number of moles multiplied by Cv, where Cv is the molar heat capacity at constant volume। molar heat capacity at constant volume, and this was molar heat capacity at constant pressure। okay, so we have written these four terms। so this is called the specific heat, that small cp, and this capital Cp is called the molar heat capacity, and this is the specific heat capacity। okay, and this capital C, what is this? This is called heat capacity। this is called heat capacity of a system or of a gas। तो अब इसमें डिफरेंस क्या है? मान लो मैं कैपिटल C को क्या लिख सकता हूँ, Q अपॉन डेल्टा T। सो वी कैन से दैट दिस हीट कैपेसिटी of a gas is nothing but the heat required to raise the temperature of the gas by 1 degree Celsius। okay, and this C is an extensive property। this capital C is an extensive property। why? because capital C is nothing but M into CV or N into CV। so capital C, what is capital C? it is nothing but say M into CV or number of moles N into capital CV। so this value of capital C, that is the heat capacity, depends on the mass of the gas or the number of moles of the gas। that is why this is an extensive property, while your this Cp and Cv, or this small p Cp and small Cv, they are the intensive properties। okay, because they do not depend on the number of moles of the gas taken or the mass of the gas taken। okay, so just we will again write these things। so we can say that what is small Cp, that is the specific heat capacity, I can write at Q at constant pressure divided by mass of the gas into delta T, and capital Cp, that is the molar heat capacity, is equal to Qp divided by number of moles of gas multiplied by delta T। okay, and this is called the specific heat capacity of gas because it is per unit mass, and this is called the molar heat capacity of gas because it is per unit number of moles। Cp means at constant pressure and this is also at constant pressure। okay, so we can say that this small Cp and this capital Cp, they are intensive properties। they are intensive properties। okay, because they do not depend on the size of the system or on the mass of the system। okay, or we can define this capital Cp as the heat required to raise the temperature of 1 mole of a gas by 1 degree Celsius. Okay, suppose I keep n equal to 1 mole and delta T equal to 1 degree Celsius, and what will be capital Cp? Will be Qp, that is the heat supplied at constant pressure. So the definition of molar heat capacity at constant pressure is, it is the heat required at constant pressure to raise the temperature of 1 mole of a gas by 1 degree Celsius. That means the process should be carried out isobarically or at constant pressure. In this case, if I write small Cp, this is the heat required to raise the temperature of 1 gram of the gas. Here 1 mole was taken and here 1 gram of the gas by 1 degree Celsius. Then this small Cp equal to capital, this is heat supplied at constant pressure. So we can write that m into small m into this Cp equal to number of moles multiplied by capital Cp. Okay, because they are both equal to Q upon delta T. Okay, so if I take 1 mole of the gas, then for 1 mole of the gas the mass is molar mass of the gas multiplied by small Cp equal to number of mole is 1, so it is capital Cp. So this is the relation between molar heat capacity and specific heat of the gas. Okay, and similarly will be the case for this specific heat at constant volume, and that is the molar heat capacity at constant volume. So this is just the relationship between small Cp and capital Cp, that is the specific heat capacity and the molar heat capacity of the gas. Now we will go in details about the molar heat capacity, that is capital Cp and capital Cv. As we know that heat supplied at constant pressure equal to m into Cp into delta T, and heat supplied at constant volume equal to n into Cv into delta T, where capital Cp is the molar heat capacity at constant pressure and capital Cv is the molar heat capacity at constant volume, n is the number of moles of the gas. Now, as per this first law of thermodynamics, we know that increase in internal energy, the change in internal energy of a gas is equal to Q plus W. That is the heat supplied to the gas plus work done on the gas. Okay, in this case, suppose I carry out the process at constant volume. Okay, then at constant volume work done is 0. So I can write delta U equal to QV, that is heat supplied at constant volume equal to increase in internal energy of the gas. Okay, so this I can write as delta U equal to NCV delta T. So this is another formula. Okay, so this is about the molar heat capacity at constant volume. So we have this formula, that is heat supplied at constant volume equal to delta U, that is the increase in internal energy of the gas, equal to NCV delta T. Okay, now there is another formula for Qp, that is NCP delta T. In this case, when we supply the heat to the gas at constant pressure, the volume of the gas also gets changed, or rather volume gets increased. So gas is also doing some work, so its PV value will change. In this case, we write this as delta H, where H is the enthalpy. So heat supplied at constant pressure equal to NCP delta T is equal to increase in enthalpy or the change in enthalpy of the gas, where H is nothing but U plus PV. This is the enthalpy. U is the internal energy of the gas, okay, and P is the pressure and V is the volume of the gas. So these two formulas we will use frequently in our calculations, that is QV equal to NCV delta T equal to delta U, that is increase in internal energy, and QP equal to NCP delta T equal to delta H, that is the increase in enthalpy of the gas. If I give you a numerical that 2 moles of hydrogen gas is heated in a closed vessel, that means it is at constant volume from say 100 degrees Celsius to 200 degrees Celsius. Then what is there? Change in internal energy, that is delta U. What is the change in internal energy? That is delta U. Okay. Change in U, that is delta U is to be determined. So how we will do? We will apply this formula, delta U equal to N CV delta T. N is 2 moles and CV for hydrogen. Hydrogen is a diatomic gas, and we know that the CV value is equal to degree of freedom multiplied by R by 2, or we can say F by 2 R. Okay. In case of diatomic gas, the degrees of freedom is 5, that is 3 translational and 2 rotational. So what will be CV? CV will be equal to 5 by 2 R. So we will write 5 by 2 R, and R is nothing but 8.3 joule per mole Kelvin multiplied by delta T is 200 minus 100, that is 100 degrees Celsius. So by this we can find the value of this delta U, and that will be coming in joules. So that is how you can find the value of increase in internal energy or the change in internal energy of the gas if we know the temperature by which the gas is heated. Now we will write the various expressions involving Cp and Cv. The one expression is Cp minus Cv equal to R, where R is the ideal gas constant. Okay, and there is one more, that is Cp divided by Cv equal to gamma. This is called the specific heat ratio. And we know that Cv is equal to F by 2 R, where F is the number of degrees of freedom for the gas taken, and this value of F depends on the atomicity of the gas. Depends on atomicity of gas. That is, say if it is a monoatomic gas, then degrees of freedom is 3, that is all 3 are translational degrees of freedom. If it is a diatomic gas, then degrees of freedom is 5, that is 3 translational plus 2 rotational. If it is a polyatomic gas, that is more than 3 atoms, then degrees of freedom is 6, that is 3 translational plus 3 rotational. Okay, so by this we can find the value of Cv for these various gases, and we are talking about the ideal gases. All these gases are ideal gases. Okay, so that is how we can find the value of Cv, and by this formula we can find the value of Cp, and then we can find the heat supplied to the gas or absorbed by the gas at constant pressure and at constant volume by the formulas which we have discussed earlier. So if I write the general formula, then I can say at constant volume, Q at constant volume equal to delta U is equal to N CV delta T, where N is the number of moles. Instead of N CV, I can write F by 2R into delta T. So this is the formula for heat supplied at or heat exchanged at constant volume. If I write the formula for QP, that will be delta H, that is the increase in enthalpy of the gas, and that will be, instead of this I will write Cp, that is NCP delta T, and here N into Cp is Cv plus R, so it will be F by 2 plus 1 R into delta T. So this is the another formula. So this is one formula for constant volume, and this is another formula at constant pressure. So these two formulas we will use frequently in our numericals. Okay, and degrees of freedom I have already told, it is nothing but 3 for monoatomic like helium, neon, etc. And it is equal to how much? 5 for diatomic like hydrogen, nitrogen, oxygen, etc. And F is equal to 6 for polyatomic like sulfur dioxide, sulfur trioxide, okay, etc. So you note down these formulas, they are very important and they will be used frequently in our numericals whenever we want to find out the heat supplied to a gas at constant pressure and the heat supplied to the gas at a constant volume, or this is also a delta U, that is the increase in internal energy of the gas if it is at constant volume, and if the process is carried out at constant pressure, then it is the increase in enthalpy of the gas. And gamma, we know it is Cp by Cv, and this can be written as Cp, that is nothing but what? This is the value of Cp, F by 2 plus 1 divided by Cv, that is F by 2. For this we can write as 1 plus 2 by F. So this is the formula for gamma. This you can note down. So gamma is equal to 1 plus 2 by F, where F is the number of degrees of freedom that depends on the nature of gas. Now we will take two past year questions that have been asked in JEE exam or BITSET exam. First I will take the question that was asked in JEE, that is 2019 main. And this question is 5 moles of an ideal gas, 5 moles of an ideal gas at 100 Kelvin are allowed, they are allowed to undergo reversible compression if its temperature becomes, till its temperature becomes 200 Kelvin. That means the temperature rise is 100 Kelvin, and the Cv value that is given to us, that is molar heat capacity at constant volume is 28 joule per mole Kelvin. It is given to us. and what we have to find out is we have to calculate delta U and delta PV. These two things we have to find out. So what we will do, first we will write the equation delta U. It was nothing but NCV delta T. This was the general formula. Okay, CV is already given to us and number of moles is 5. So 5 into 28 into delta T. Delta T is 200 minus 100. So this value we can find out this delta U. Okay, this will be 500 into 28, this many joules. Okay, and we have to find out the delta PV also, and we know that H equal to U plus PV, that is the enthalpy. So what will be delta H? Will be delta U plus delta of PV. So what is delta PV? Delta PV will be equal to delta H minus delta U. Okay, so delta U we have already calculated. Now what we will calculate is delta H, and what is delta H is nothing but NCP delta T. Okay, and CP, what is CP? CP equal to CV plus R. CV is given to us, that is 28 plus R. R we can take around 8.3 joule per mole Kelvin. So we will get 36.3, that is the value of CP. Now we can put the value of CP in this equation, and delta T is given to us, N is the number of moles, so we can find out the value of delta H. Once we know the delta H, then delta H minus delta U will give us the value of delta PV. That is how we can calculate this out. One more example we will take, that was asked in the bit set exam, then we will conclude this session. Okay. Now this numerical was asked in one of the bit set exam. This is says the heat change. This is for a reaction. The heat change, that is delta H. The heat change, that is delta H we say. For the following reaction, at 298 Kelvin and constant pressure, it is given that pressure is constant for this reaction, is plus 7.3 kilocalorie. That means this much kilocalorie is absorbed during the process. Okay, and the reaction given is A2B solid, it gives 2A solid plus half B2 gas. So this is the reaction which is given to us, and what we have to find out is the heat change at constant volume. The heat change at constant volume will be, four options are given to us, that is A is 7.0 kilocalorie, B is more than 7.3 kilocalorie, C is 0, and D is none of the above. So four options are given to us for this answer. So what we will do? Okay, so what is required is the heat change at constant volume. We know that heat change at constant volume is nothing but delta U, which is nothing but NCV delta T. Okay, and we have been given the value of at constant pressure, that is what is given to us is delta H, that is QP is delta H, it is given to us as 7.3 kilocalorie. Okay, and we know the relation between delta H and delta U is delta H equal to delta U plus delta of PV. and delta of PV I can write as PV equal to nRT. Okay, so delta PV is nothing but delta of nRT. Here temperature is constant at 298 Kelvin, so this I can write as delta U plus delta Ng, that is gas. It is a gas is formed as one of the products, so I write delta Ng into RT. Okay, and what we have to find out is the value of heat change at constant volume. So delta U will be nothing but delta H minus delta Ng into RT. Here delta H is already given to us, that is heat change at constant pressure. It is given to us 7.3, so I will write 7.3 minus delta Ng. What is the change in number of moles? That is half, because all these are solid state, so only half. So delta Ng will be equal to 1 by 2, that is number of moles of gaseous products minus number of moles of gaseous reactants, so that is half multiplied by R. R is known to us, that is in kilocalorie. I will write 2 calorie, or we can say 2 into 10 to the power minus 3 kilocalorie, that is the value of R. This will be in kilocalorie per mole per Kelvin, and multiply by temperature, that is 298 Kelvin, which I can write around 300 Kelvin. For approximation I will take 300 Kelvin. Okay, so this will become 7.3 minus this 2 will cancel out, and this will be 0.3, so it is 7 kilocalorie. Okay, so the answer is 7 kilocalorie, that is option A is correct. So that is how we can find out the value of heat change at constant volume or heat change at constant pressure. If one is given to us, the other can be found out. Okay, so to summarize, we have used the following formulas that you have to note down. One is heat at constant volume. Heat exchange at constant volume is nothing but increase in internal energy or change in internal energy of the gas is equal to N CV delta T, where CV is the molar heat capacity at constant volume, and the value of CV is nothing but F by 2 into R, where F is the number of degrees of freedom and F is equal to 3 for monoatomic gases like helium, neon, etc. monoatomic gases, and F equal to 5 for diatomic gases like oxygen, hydrogen, etc. and F equal to 6 for polyatomic gases like sulfuric, SO2, SO3, etc. Okay, so you can find the value of CV, and R is nothing but 2 calorie per gram mole into per Kelvin, or it can be written as 8.3 joule per mole per Kelvin. This is calorie per mole Kelvin, or 8.3 joule per mole Kelvin. And the other equation was heat supply or heat exchange at constant pressure. It is nothing but delta H, where H is the enthalpy. So delta H is the change in enthalpy, equal to N into Cp into delta T. Once we know the value of Cv, we can find the value of Cp, that is nothing but Cv plus R. Okay, so we can write that Cp will be Cv, that is F by 2 plus 1 into R. So that is how we can find the value of this Cp, and once we know the value of Cp, we can find the enthalpy change of the gas. If it is heated by a temperature of delta T, N moles are heated by a temperature of delta T at constant pressure, then this we can find out what is the heat to be given to the Yes. Okay. With this we conclude this session. If you have any doubts, then we will discuss in the next session. Till then, I wish you all the best. Thank you.